Okay, hey, welcome back. Now we're going to sort of re-envision the integral in order to find volume of objects. So before we're just finding area. This will be kind of interesting. We won't use it too much in the future unless you have a teacher that kind of wants to pick on you. But I probably won't be using it too much, not even in like Calc 3 or anything. Anyways, let's think about what the Riemann sum was and that sort of thing, and then we'll kind of expand upon that idea. So the most important thing, at least for me, is this ability to re-envision the Riemann sum to sort of to use it to your own ends. Like later on, we'll find that we, instead of just adding up rectangles, we can add up other things. Well, here, that's what we're going to do. Instead of adding up rectangles, we're going to add up the volumes of disks or washers. Later on, we'll find we can add up vectors, we can add up dot products of vectors, all kinds of cool things once we get to Calc 3. That's pretty far way away, but here you'll start getting a feeling for being able to kind of get in under the hood of the integral and make it do what you want it to do, okay? Okay, so here we go. I'll begin with this sort of idea of integration as accumulation. And I even talked about it a little in the last section, accumulation, sorry. So you're thinking of this Riemann man kind of running across the x-axis, collecting all these rectangle areas. So he's running across like this. Let's do sort of curve like this. And here's a generic rectangle here. But the idea is he's basically running across, find the area of all these rectangles, adding them up, and then we take the limit as the number of rectangles goes to infinity, and that gives us the integral that we all love and know and love, right? So he's getting all these v sub i's, where well, actually right now they're a sub i's, right? They're areas. We want to change that eventually into volumes. Right now they're just a sub i's. Okay, so let's say this is f of x. So a sub I would be f of x sub I, whatever your particular value is for this position. And then there's a width for the rectangle's base. So basically base times height, right? It's just geometry, basic geometry. So times change in x, and the Riemann man is running across, adding all these little elements up, these delta a sub i's, and then we take the limit as the number of rectangles goes to infinity, and we end up with our integral of f of x dx, right? We'll go from A to B. Okay, great. Now we want to re-envision this integral. We want to, instead of collecting areas of rectangles, we're going to collect volumes. Let's take a look at what we're going to do. So it's kind of the same picture, kind of the same Riemann man going in the same direction. He's got his bag here. He's going to be collecting volumes this time, so delta v sub i's. And I'll keep the original picture kind of the same function, f of x. But the way we interpret these rectangles is going to be a little bit different. Okay, so let me draw in a generic rectangle here at some position x sub I. Okay. And of course, again, there's this change in x width, and he's collecting all the rectangles. Pull a bunch of them. I'm just going to smush one in here. Okay, so now what we're going to do is imagine taking that red rectangle, or even the whole region here, and rotating it about the x-axis. We're going to rotate it like this. Okay. And I'll just play around with that one red rectangle there. And as it rotates, what it's going to do is it's going to create this disk object. Okay. Have to be a little artistic to be able to do this. where did the rectangle go? It's in there. It's sitting right here. Okay. And we want the area, the volume of that disk. And what it's not really a disk, it's more like a smushed cylinder, to be honest with you. So we know the formula for the volume of a cylinder. The volume of a cylinder is just pi r squared h. It's just the area of the base times the height. And we could put all of this in terms of x and f of x. Let's take this thing and kind of put it in our usual way of thinking of it, kind of laying flat, like more like a Pepsi can or something like that. Okay, so here's the thing laying flat. We're going to be able to figure out this radius. Okay, that radius distance is given by f of x, right? So this position right here, if you look on the left, that point right there is x sub I comma f of x sub I. So the height of that rectangle, and again, the rectangle is sitting like right here inside of our cylinder thing, our disk, or if you'd rather, it's sitting right here now. The height of that rectangle then is just f of x sub I. So you know the radius. We also can tell the height, right? This dimension right here will be the height. And what is that in terms of our picture? Well, that's the change in x. Okay? So this dimension is just change in x. And so we can rewrite the volume for this particular slab, I guess. V sub I, we'll call it, as pi times f of x sub I squared times change in x. Okay? And that becomes the thing that our Riemann man now is accumulating in the integrals. So the Riemann man, you know, usually we did it with the geometry of a rectangle back here. Now we're reinterpreting what we're doing as accumulating volumes. So the Riemann man is, what is he doing? He's running across, he's adding up all of these v sub i's, or call them delta v sub i's, I guess. And then we're going to take the limit as the number of them goes to infinity, and we end up with our nice little integral. This time there's going to be a pi in front of it because of that pi r squared h thing. Again, we're going from some a to some b on the picture, which I didn't draw in. And then you have your f of x squared dx. Okay, that's really it for the washer, or sorry, the disk method. Let's look at what the book has. So yeah, they kind of do a little picture. So I mean, ultimately, what you're finding the volume of is just what you see if you would rotate this region here on the left here. If you rotated that region about the x-axis, that's the thing you're finding the volume of. So in this case, it would look like a kind of a vase or something like that. So something like this. Ugh, sorry if that's not perfect, but there it is. And kind of put it in 3 dimensions by putting another axis on here. So that would be that thing. And then the volumes are just, you know, we cut this into a bunch of slabs, and we're figuring out the volume of the slabs, which in this case we're calling disks. And at the end of the day, it's just this easy formula, but you could see the geometry, the geometry, the formula for volume there still. So it's pi r squared h. It's kind of still in there. Okay. So basically the Riemann man is adding up all these cylinders here in figure 7.14, and then we smooth it out with the limit and find the actual, yeah, so there's our integral, our new integration formula. And it's just from reinterpreting the thing the Riemann man is accumulating as a volume. There's 2 orientations again. You can have the vertical rectangles or the horizontal rectangles. And you just pick the orientation. Well, they'll tell you. They'll say you have to rotate about the x-axis or the y-axis. Your rectangles will always be, in this case, perpendicular to the axis of rotation. Okay, so maybe I should write that down. Your rectangles will be perpendicular to your axis of rotation. Okay, so in my original picture, the first problem, the axis of rotation was the x-axis. Okay, so this is an x-axis rotate. But you can easily also do a y-axis rotate. So y-axis rotation. And in that case, you'll probably, maybe you'll have some sort of parabola here that you want to rotate this region here about the y-axis. Let's give this guy a name, call it g of y. And in this orientation, the Riemann man is going up the flagpole again. Okay, this time he's collecting volumes, so delta v's sub i's. And the rectangles for the cross sections of those disks will be oriented in the way that red rectangle there is oriented. And so you'll be going from some value c to some other value d. It's the same formula except with y. So g of y squared dy. Okay. Okay, so I guess you're kind of forced in this in these scenarios to either use x or y based off of what axis they want you to rotate on, I believe. Okay, so let's look at example 1. They want us to revolve the region bounded by the graph of the square root of sine x. I'm not exactly sure how I would graph that, but going from 0 to pi, it's probably, because all the values of sine of x are positive in there, it's going to have kind of that sine look to it, okay? And then we're rotating about the x-axis. The book tells us it wants an x-axis rotate, okay? What I like to do is identify my rectangle and then do my formula based off the rectangle. In this orientation, I'm running like this. My function here is y equals square root sine x. And so the radius that I need, so the formula is pi r squared h, right? And the r is going to be the height of that rectangle. So in this case, the radius is square root sine x. And you could kind of envision what that would look like if you rotated it about the x-axis. It would be kind of like a football type thingamajig, looking like this. And then you put some extra axes to kind of make it look three-dimensional. But, like that. They do have a nice little picture for you in the book. Yeah. Okay. So to get the area, I'm going from 0 to pi, and I just plop it into my integral of the day. So pi r squared. So pi times the square root of sine x squared dx. I'm going from 0 to pi. So I get pi integral of sine x, the square of the square root, make the square root go away. And then this will be negative pi cosine x from 0 to pi. Plugging in pi first, cosine of pi is -1, and then plugging in 0, that's just 1. So it'll be -2 times negative pi is positive 2 pi. Should be the volume then of that region. Okay, and you can see that's what they got. Okay, great. Let's see what else they got for us. Rotating about a line that is not the coordinate axis. So this is a shifted axis of rotation. Maybe I should make a new section for this. So we'll make this section 2. Shifted axis of rotation. Whenever I pull these off, I kind of think in terms of differences of rectangles. And that will give me kind of my radius. Okay, so we got example 2 to play around with. Let's see what happens. So they have f of x equals 2 minus x squared. And then they also want the line g of x equals 1. And we want to rotate about the line y equals 1. Okay, so let's graph the thing. 2 minus x squared, so that will flip the graph of a parabola upside down and then shift it up 2 places. Okay, so 1, 2, and then you'll get plus or minus square root 2 for intercepts, so it'll be right there. Okay, g of x equals 1, that's just a horizontal line going through 1. And that's the line we also want to rotate about. So I want to rotate about this thing. And the resulting object will be like a football type shape. So sort of like that. Okay, so pretty clear, I think, what that thing looks like. I hope that's clear. Okay. Right, so I need to figure out the radius of this thing, my r of x. And what I do, again, I think in terms of these rectangles and my Riemann man. So he's running across. Let me put the rectangle in red. So I made the length of that rectangle for any x position. So right now, let's say it's just at x sub I. Okay? So that will give me my radius, my r of x. Okay, so what is the length of that rectangle for any x sub I? Well, it's a difference, right? It's a difference between, let me put them in, I guess, yellow. It's a difference between this height to the parabola and then the distance to the blue line, right? So your function r of x you can think of as the distance to the function, which is 2 minus x squared, and then minus the distance to the line, which is just 1. So you end up with 1 minus x squared as a formula to give you the length of those red rectangles. And then all you have to do is integrate from, so it's pi r squared, and we're integrating from, I guess, the intersection between those. So what is the intersection? I need to set f of x equal to g of x. So 2 minus x squared over here to the left equals 1. X squared minus 1 is 0, so plus minus 1. You can multiply it by 2 and just integrate from 0 to 1 if you want, because it's going to be symmetric. And then our radius, so 1 minus x squared dx. Okay, so let's go ahead and FOIL that. So you get 1 minus 2x squared minus x to the 4th dx. And then I got 2 pi times x minus 2x cubed all over 3 minus x to the 5th over 5 from 0 to 1. And then you got 2 pi times 1 minus 2/3 minus 1/5 minus 0. And then 2 pi times, I guess, 15/15 minus 10/15 minus 3/15. So that would be 2 pi times 5 minus 2/15. So I'm thinking 4/15, 4 pi over 15, unless I made some idiotic mistake, which is highly probable. And I made a mistake, of course. Life wouldn't be complete unless I made some error. So they need a plus on that last, oh, this is plus. Plus. So this will be 2 pi times 15 minus 10 is 5/15 plus 3, so that'd be 8/15. And then, of course, that's a 16/15 pi. Did they give us one with the other orientation? Y orientation? I don't think so. We did example 1, and then we just did example 2. Let's find one in the homework that has the other orientation, the Y orientation. So this guy. Set up and evaluate the integral of the volume from revolving the region about the Y. I mean, that's pretty easy. I don't know. Sure. Let's make this on the video quiz too, as well, and get it out of the way before I forget. So this is the second question in video set number 3, video quiz set number 3. And for me, it is WebAssign Problem 3. If this isn't challenging enough, you could go look in your own WebAssign and just do the problem with your particular number. I mean, not challenging, but annoying. Because at least then you could do your problem and get it right and everything, if you want to put that in your video quiz instead of my version with the 7. So that red number is auto-generated. It's different for everybody. It's supposed to enhance security so people can't cheat. I don't know. Anyways, yeah, let's try this guy. So this is the video quiz question. We still have to do the washer method, so it's not like this is the end, but okay, so give us x equals negative y squared plus 7y. It looks like they're kind of telling you automatically what the region, what the limits on your integral should be. And I mean, there's not much to it, right? So you're just, your Riemann man is going in this direction up the flagpole and accumulating the area underneath this curve from, it looks like you're going from 1 to maybe 5 on the y-axis. I would not do it with regards to x, because you're going to have to split it into 2 different curves, and that would be a nice nightmare. You probably have to complete the square, and oh my gosh, so no. Let's see, so I think it's going from 1 to 7 on the y-axis. So your little rectangle is this. And so this time your r, it's r of y as opposed to r of x. So r of y is negative y squared plus 7y. And then your integral from 1 to 7, we have pi out there, and you have a negative y squared plus 7y squared dy. And then it's just a matter of integrating that thing. So pi times the integral, negative y to the 4th minus 14y cubed plus 49y squared. This should be positive. Why do I keep doing that? Dy, negative times a negative is positive. Power rule it. So you get y to the 5th over 5 minus 14y to the 4th over 4. Or if you'd rather, 7y to the 4th over 2. Plus 49, they're not being nice, are they? Y cubed over 3, not giving us nice numbers like that. That's kind of mean. Pi, oh, look at that. Um, 7 to the 5th. 16,807 over 5 minus, that's 7 to the 5th again. 16,807 over 2 plus, that's also 7 to the 5th. 16,807 over 3 minus, plug 1 in there. 1/5 minus 7 halves plus 49 thirds. And if you don't mind, I think I'm just going to go the Wolfram deal with it. Let's see if they need an approximation first. They don't want one. So if they don't say the number of decimal places that they want, that means they don't want an approximation for their answer. And you're going to have to get a fraction or something like that. Let's go to Wolfram and see how nice they are about it. So 16807 over 5 minus 16807 over 2 plus 16807 over 3 minus 1/5 plus 7 halves minus 9 thirds. 2736 over 5 pi. Okay. So let's see if they like it. 2736 over 5. You just type pi in. Yay. Okay. Let's move on. Let's see what else they got. I think the next part then is going to be the washer method. So that you use the washer method when you have a hole in your object. So when you rotate the thing and you see a hole in it, then it's the washer method. Okay, so section 4, let's set this up again like we did before. So again, kind of remind yourself of how the accumulation process is working. Here we're going to be rotating some region generally given by 2 curves. So for this method, you basically need 2 R functions, 2 radius functions. I'll say 2 radii. Need 2 radii. Okay. So you're going to have some f of x function and then probably some g of x function, and then you're rotating that region about the x-axis or the y-axis. In this case, we're doing the x-axis. So let's call this f of x, this one g of x, and then you have all this region. And basically, it'll look like a solid kind of vase with a hole drilled through it once you rotate it. Let's just look at one particular rectangle here that our Riemann man will be accumulating. So the Riemann dude is going in this direction this time and collecting up these volumes, these delta v's. All right, so this one particular guy, maybe I shouldn't do that so fast. This one particular guy, this red rectangle, if I were to rotate that thing, it's going to be a disc but with a hole in it, right? So the washer, like you would use when you're screwing in bolts. Okay, so I'm trying to do my best to draw it. It's got a hole in it. Okay. And so that red cross section is going to be like right here now. Okay. All right, so again, we need the volume of this thing, and I'm going to lay it flat so we can kind of think about it in terms of everything and sort of this orientation we're used to. So again, it's basically the formula of a cylinder, but there's a hole in it. So it's to find the volume of this thing, it'll be pi r 2 squared h minus pi r1 squared h. So there's going to be 2 radii. And you can figure out the radii from the g of x and the f of x, right? So the smaller radius is from your g function, so that would be g of x sub I right there. And then the larger radius is going to be from your f of x function, so that would be f of x sub I right here. And again, the h is just going to be the change in x width of your particular rectangle. Okay, so you get a change in x there. Okay, so this dimension over here is going to be your change in x. And so the thing that the guy is running through and accumulating now, the Riemann man, these delta v sub i's will be pi, the top one f of x sub I squared times change in x minus pi times g of x sub I squared times change in x, and of course we can simplify that into pi times f of x sub I minus g of x sub I, both of those squared, times change in x, and then the Riemann man is going to accumulate all of those to get the approximation of the entire object, and then we take the limit as the number of those objects goes to infinity, and we end up with our new integral pi times f of x squared minus g of x squared dx. Okay. Okay, as usual, you can have 2 orientations. You can have this orientation or the one where the Riemann man is running up the flagpole. Let's take a look at whatever example they have for us. This is example 3. Find the volume of the solid formed by revolving the regions of the graphs of y equals square root x and y equals x squared about the x-axis. So let's get a picture. So x squared, and I guess they're going to intersect at 1, 1, aren't they? So let's make it a little bigger. We have this. So the x squared is concave up, and then the square root x is concave down. We want to rotate this region about the x-axis. Okay? And you'll note that they do intersect there at 1, 1. If you set the two equations equal to each other, you would get that. Square both sides, you get x to the 4th equals x. And then you could set it equal to 0. Factor out an x. And then x is 0, that's this point. And then x cubed minus 1 is 0, so x cubed equals 1. The cube root on both sides, x is just equal to 1, so that's this other point. Okay. So you could kind of figure that out if you needed to. We want to rotate it about the x-axis. So you'll see there, if you're dealing with the object, it's kind of like a cone thing, but on the inside it's kind of scooped out, right? So it's kind of scooped out a little bit on the inside. And whenever that's the case, so you can basically put your hand in the object. If you're looking on the right, you'll see what it looks like in all of its glory. If you can put your hand in it, in this case you can't put your hand all the way through it, but you can still put your hand in it. In those cases, you're using a washer method. Okay, let's get our rectangle. So there's going to be 2 radii. The bigger radius, I'll call that big R of x. Okay. That's going to be from x squared, and then there's a little r of x, and in this case we'll do that in blue. That will be the distance to the bottom curve. Okay. So it's basically you're finding the volume of the kind of the big thing, and then you're just subtracting away the volume of the little thing. Okay, so r of x, I guess I should do that in blue. Little r of x here is from the square root of x. Okay, then we're integrating from 0 to 1. We need a pi, 0 to 1, a big R of x squared, and then minus little r of x squared dx. So we'll have pi times the integral x to the 4th minus x dx, and then power rule, and get the antiderivative. So pi times x to the 5th over 5 minus x squared over 2. From 0 to 1, and then we're going 1/5 minus 1/2. Okay, so that would be 2/10 minus 5/10, which isn't working for me because it's going to give me a negative, and we're talking about volume, and volume isn't negative. What did I do wrong? Oh, I got big R of x is the square root function. Sorry, oh bloody hell. Sorry. This is the top one is this. Thank you. The top curve is the square root function. So the red one should be the square root of x. And then the bottom one is the x squared, sorry. So the x squared is concave up. The square root of x, the concave down one, is on the top. Okay, and now my rectangles are out of place. So the red one is the square root of x, it's that one, and then the blue one, sorry, I apologize, is the one below it. So everything is screwy. Let me get all this junk out of the way. Okay, so it should be the integral pi times the integral square root of x squared. Yeah, you shouldn't get a negative for your answers. because you're finding volume, and volume isn't going to be negative for us. Okay, so equals pi times x minus x to the fourth dx, and then power rules, pi x squared over 2 minus x to the fifth over 5, from 0 to 1, and that will equal pi times 1/2 minus 1/5, and then we'll get our answer, right? So this would be 5/10, 2/10, so 3/10 pi. Sorry about that. Did they even figure it out? Yeah, there it is, 3 pi over 10. Okay, this one is kind of weird. We have like 2 parts to it. So, example 4. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis this time. Okay, so x squared plus 1 looks like this, and it goes through y equals 1 right here. X equals 0, it would be the y-axis. X equals 1, vertical line through x equals 1, and then x equals 0 is, yeah, I already got x equals 0, that's the y-axis. Y equals 0 is the x-axis, so that's this line. And then the region we want to rotate would be this region here. Okay. So our Riemann man is going to be oriented in this direction because we're rotating about the y-axis. Okay, let's put our rectangles there. And so there's an additional issue here. In the first region, the top curve is x equals 1, the bottom curve is x equals 0. But then once you get to right here, and I'll draw it in black here, the top and the bottom curve change, right? The top curve is still x equals 1, but the bottom curve will become that parabola. Okay, so you see it's variable in that region, and it's dependent on where the parabola is. So let's get our 2 formulas. So our first r of y, so I guess I can go region 1 for this bottom region. I'll put blue. This is region 1. For that region, my big R of y is going to be 1. And I guess there isn't a little r of y, so it's not really even a washer method at that point, because when you rotate, there's not going to be a hole in it in any way. So you could just do big R of y is 1. If you want little r of y, it would be 0. Right? Then region 2. For that rectangle, you're thinking in as a difference, right? So you have the distance to the outer curve, which is well, I guess you're not even thinking in terms of a difference. It's just 2 different rectangles altogether. The big rectangle, big R of y, is going to be 1, and then the little r of y is going to be that parabola. But you're going to have to put it in terms of, right? So that would be, the big R of y is this, the distance to the line. The little r of y is the distance to the parabola. So this distance. So I need to take my y equals formula and solve it for x. And so I get x squared equals y minus 1. In other words, x equals the square root, plus or minus square root of y minus 1, but I want the plus arm of it. So I guess this yellow arm is going to be the square root of y minus 1. And that also then becomes your little radius. Okay, so you have 2 regions. You're going to need 2 integrals. So first, the Riemann man is doing basically a disk method. You just have 1 squared dy going from 0 to this position, which is 1. And then plus the integral pi times 1 to all the way to whatever this point is. So I have to set the 2 equations equal to each other. X equals 1. You could just basically do a substitution into here. from x equals 1, you get y equals 1 plus 1, which would be 2. So this point right here is 1 comma 2. So you're going from 1 to 2 then, and in that case you have 1 squared minus the square root of y minus 1 squared dy. Let's see if I set it up correctly. Yeah. Okay, so now let's go ahead and simplify this thing. So I got pi. Okay, so hopefully that was obvious. There's two regions. There's this bottom region, which I'm calling R1, and then there was a secondary region in here, this little wedge, which I'm calling R2. Okay. R1, when I rotated that's just a disk method. R2, though, will have kind of a hole in it, right? So if you look at their picture, you see there's kind of an impression in the cylinder. So you need to subtract away that part of it. And, okay, so let's go to our integrals. So 1 dy, I'm just simplifying. Plus pi times the integral of 1 minus, this will become y minus 1 dy. So this will be pi times y, integrated from 0 to 1, plus pi times plus minus plus. So that would be, this thing here is going to be 2 minus y. And then when I integrate it, I get 2y minus y squared over 2, 1 to 2. And then I'm going to have pi times 1 minus 0 plus pi times 4 minus 4 over 2 is 2 minus, plugging in 1, 2 minus 1/2. So this will be pi plus pi times 2 minus 2 plus 1/2. So pi plus pi over 2. So 3 pi over 2 for the volume of that thing. Okay, so did a little technology, some manufacturing stuff. We'll see this problem in WebAssign, so let me do the WebAssign version of this and probably make that one our video quiz. Okay, so manufacturer is drilling through the center of a metal sphere of radius r. And this thing has a hole of radius r. Find the volume of the resulting ring. Okay, so what problem is this? Did I already do a video quiz? Seems like maybe I already did. Oh, I did. I did a video quiz already. All right, never mind. We'll do this problem anyways, though, because everybody always asks me about it, so we might as well do it. This is problem 13. I think everybody's answer is going to be the same. But they say they have like a ball bearing or something, a metal sphere, and it has a radius r. So you can model that with a circle, equation of a circle, x squared plus y squared equals big R squared. Okay. So you have a circle of radius r, big R. So this point would be big R comma 0. Then they're drilling a hole through it that has radius little r. Okay. So they're drilling this hole, and so this would be y equals little r. And my picture isn't very good, so I'm going to get rid of it a little bit. Sorry. So I'm going to draw it again so it's more obvious what we kind of need to do eventually. Okay. So I'm going to orient it in this way so that I'm rotating it. I'm going to rotate it about the x-axis. What they want to know is the volume of the resulting ring part. Okay, so it's basically the ball bearing, subtract away the hole in the middle. Right, so if I think about the Riemann man running and collecting information here, the rectangles this person is going to be collecting are going to have this, they're going to look like that. Okay. So I need a formula for those, And not only that, I need to know where I'm going from. Like the Riemann man is going from x equals whatever, this point, to this point here. Okay. I know the formula for the circle already. That's this guy up here. X squared plus y squared is r squared. In particular, I'll have a big radius, big R of x, but I'm not going to call it big R of x because I already have this big capital R floating about. So I'll just say the big radius B of x. I need to solve this thing for x, so I'll have y equals square root of r squared minus x squared. It'll be a plus minus, but I just want the top part. So this will be square root of big R squared minus x squared. And then I'll have a little radius, let's call that L of x. And the little radius, of course, is just going to be r, little r. And then I need the, again, I need to know where the Riemann man is running from. So this point here to this point here. And basically you could set, you know, this, I need this, basically the x coordinate of that point, right? So it's going to be x comma little r. So to figure out the x coordinate, all I have to do is take that little r and plop it into this formula and solve for x. Okay? So I'll have x squared plus little r squared equals big R squared. And so x squared will equal big R squared minus little r squared. And so x will be plus minus. I want the positive one over here because I'm going to end up just figuring out this half of it and then multiplying it by 2, and that'll give me my answer. So this will be big R squared minus little r squared. And so my Riemann man is going to be running from 0 to the square root of big R squared minus little r squared. There'll be a pi out in front. And so the big radius squared will be square root of big R squared minus x squared, and then minus little radius squared, so it's a washer method, dx. And then I can go ahead and integrate that thing. So pi times the integral of what will be big X squared minus big R squared minus x squared minus little r squared dx. We're in terms of x, so the big R and the little r are just constants. So you can integrate those as though they were constants, and you would get big R squared x minus x cubed all over 3 minus little r squared x. And then we have to evaluate from 0 to the square root of r squared minus little r squared. So I get pi. Let's rewrite this a little bit so I can factor out an x and have big R squared minus little r squared, and then minus x cubed over 3, like that. Oh, and I'm going to have to multiply all this by 2 because I kind of cheated a little bit, and I'm just kind of rotating this region. Okay, so I'm going to slice a 2 in there for you. Sorry. So 0 to square root of big R squared minus little r squared. And so plugging stuff in, then I get big R squared minus little r squared to the 1/2 times big R squared minus little r squared minus big R squared minus little r squared now to the 1/2 cubed. So that'll be 3/2 power all over 3. And then minus 0. So if you plug 0 in there, you're just going to get a bunch of zeros. So this will be 2 pi times big R squared, let's just square there, minus little r squared. You can add the exponents on these two terms. They're both like terms. So like common, the same base, so you just add the exponents. 1/2 plus 1 is 3/2. And then minus r squared minus little r squared to the 3/2 all over 3. And then you can combine those. Those are like terms. So this would be 3 all over 3. So you get 2 pi times 2 times big R squared minus little r squared to the 3/2 all over 3. Yeah, and then that would just be 4 pi times big R squared minus little r squared to the 3/2 all over 3, I hope. All right, so let's plop that in and see if it's right. Big R squared times little r squared to the 3/2 divided by 3. Drum roll. Yay! Okay, maybe we should try one of these. Let's try this one, number 11. This one looks weird. So they give you a bunch of regions, and they want you to rotate apparently R1 about x equals 0. Okay. So region R1, this looks, maybe it's easier than I think. R1 just looks like this region here. X equals 0 is the y-axis. Okay, so I'm going in this rotation. So my Riemann man is going to be going up like this. It seems like it's just a disk problem. Okay, the end picture is going to be sort of a elliptic cone. Okay. So my function is going to be r of y. So the base of the rectangle tells you the sort of terms of your radius function. And then this line is just y equals x. So, or x equals y if you'd rather. So you could just say r of y is equal to y, and then integrate from 0 to 1. So pi y squared dy. So this would be pi y cubed over 3 from 0 to 1, which is just pi over 3. That seems too easy. Pi over 3, maybe yours is harder. I feel like this is too easy. Let's do at least one more. I want to do another one that's well, let's do one of these ones that's shifted. Okay. So number 7. And the volume of the region generated by revolving the region bounded by the graphs of the equations about the line x equals 6. So rotate about, I think it said x equals 6. Yeah. X equals 6. We have y equals x, y equals 0. I'm not going to put any weird rotations on the test. So I'll only rotate about the x or the y axis. I'm not going to punish you with these kind. But you need it for the homework, so I want to at least show you. So let's get the region. Y equals x is the diagonal. Y equals 0, of course, is the x-axis. Y equals 5, 1, 2, 3, 4, 5 is horizontal at 5. X equals 6, 1, 2, 3, 4, 5, 6 is this line. And they want to rotate about that line. Okay, so I have y is 0, that's the x-axis. Seems like I'm going to have to, if you do it with respect to x, you're going to need 2 integrals, right? Because you're going to have to split it right here. That's why you would want to do this definitely with respect to y. I don't think you could, because of the orientation. We're doing a route x equals 6. There's like no choice. You just have to do it with respect to y. That's what your rectangle is going to look like, right? So your Riemann man is going to be going up the flagpole in this direction. The radius function then, it's a solid object. If you think about it, rotating about this x equals 6, it's just a solid object, so it should be like a disk. So you need r of y. The base of the rectangle is perpendicular, would be sitting on the y-axis, so you think r of y. And then you could use a difference to get the actual value. So it'd be this length, which is 6, minus the length to the diagonal. Okay, so that difference would give you the radius. So 6 minus y. And so you have pi integral 6 minus y squared from 0 to y equals 5, apparently. And then just integrate that thing. So you get pi integral 36 minus 12y plus y squared dy. And so you get 36 pi times 36 y minus 12y squared over 2 is 6y squared plus y cubed over 3 from 0 to 5. So that'd be a nightmare to figure out. Pi 36 times 5. I'm not doing it in my head, I refuse to. 36 times 5, 90, minus 6 times 25, 50, plus 125 thirds. So pi times 30, so 90 thirds plus 125 thirds. 215 thirds. Pi. Let's see. 25, 23, pi. Yay. That's an x-axis. That's an x-axis. This is y-axis. Let's do one more where we have a different line of rotation. So let's try number, and I promise that'll be the last one. So 6. You already got your video quiz. So this time we're going about the line y equals 4. 4 rotation. The curves y equals 3 over 1 plus x, y equals 0, x equals 0, x equals 3. Let's see what the picture is. 2, 3, 4 is our rotation line. 1, 2, 3, there's a vertical at 3. X equals 0 and y equals 0, that's the x and y axes. 3 all over 1 plus x, so at 0 that will be 3. So you could literally just point plot that thing. At 3 it'll be 3/4, so it'll be right here. It'll probably be, kind of shifted down like this. X equals 3. X equals 0, y equals 0 in this thing. So it's this region we're rotating. The Riemann then, because our rectangles, the bases of them are going to be on the x-axis there. The Riemann's in that orientation. There's a hole in it, so it's a washer. So we need a big R of x and a little r of x. So for big R of x, I'm thinking this distance. Okay. So that would be 4. And then for little r of x, I'm thinking the distance to the 3 all over 1 plus x from the line of rotation, though. So that blue rectangle, you think of it as a difference of 2 rectangles, right? It's the actual distance to the line, which I'll put in yellow, and then subtract away the distance to the rational function, the 3 over the 1 plus x. Okay, so again, it's going to be 4 minus the 3 all over 1 plus x. Okay, so it's going to be a nasty one. So you got the integral from 0 to 3 of 4 squared minus 4 minus 3 all over 1 plus x squared. So you'll practice doing some integrals. So we get what? Plus integral 16 minus. So this will be 16 Minus 12 over 1 plus x minus 12 over 1 plus x is 24 all over 1 plus x, and then plus 9 all over 1 plus x squared dx. And then that will simplify a little bit. The 16s will cancel, and you'll have 24 over 1 plus x plus 9 times 1 plus x to the negative 2 dx. That should be a minus. I know I see it. Don't worry. The first one's a natural log, so that would be pi times 24 ln of 1 plus x. You can do a u sub. You don't need it though, because you won't have any constants. It would just be du is dx. And then the second guy, same there. You're not going to have any constants. Du will be dx. So be raised to the negative 1 and then divided by that. And then evaluate it on the limits. So this would be pi times 24 ln of 1 plus x plus 9 all over 1 plus x from 0 to 3. And then just evaluate it. So you get pi times 24 ln of 4 plus 9 all over 4 minus 24 ln of 1 is 0, and then plus 9. So it would be like that. So you get pi times 24 ln 4. So this would be 36 over 4. So minus 27 fourths. And then we're going to get a decimal approximation. So it says 3 decimals. And so pi times 24 ln 4 minus, oops, parentheses, minus 27 fourths. I'm getting 83 point something, 83.32. Whoops, 3 decimals, 0.318. See if that's right. And okay, I'll leave it at that then. So I think I did most of the shifted axes. Well, I guess there's one here where you have to kind of shift them around, and this one you kind of have to shift them around. But hopefully you'll be able to leapfrog from my examples into those questions. Okay, we'll leave it at that. As usual, thank you for watching, and we'll see you next time.